Welcome back, engineers. So in the previous videos, we touched upon the different types of distributed systems, leaderless, multi-leader systems. We briefly touched upon quorums and how the quorum systems can ensure that eventually all the nodes come to a convergent state, right? But we haven't really given it a formal definition, and we haven't really seen the algorithms that are actually used to achieve all this, right? So in this video, let's talk about consensus and see how different nodes eventually converge to the same state and they all come to an agreement, right? I hope you're ready. Let's get started. So let's first try to understand what is consensus. So consensus means that when multiple computer nodes agree on a single value, even if some of the nodes fail or even misbehave, right? So eventually they need to come to some common understanding, and that is what consensus means. So let's see a brief example. So let's say there are three nodes, and node 1 is proposing to have chocolate ice cream, right? And this message is sent to the other nodes, and one of the nodes say, yeah, it's a great idea, let's have it. But third node is saying, I want vanilla, right? So in these kind of situations, we need to have some kind of mechanism to bring all of them to the same state. So one of them can be a voting mechanism. And we see that chocolate is having 2 votes and vanilla is having 1 vote. So we eventually make the chocolate as a winner, and everybody should agree that it's chocolate that they are all going to have. So node 1 is saying chocolate yes, and node number 3, even though it didn't agree to the proposal in the first place, should agree now, because that's what the algorithm is all about. So eventually all of them are in agreement and they have reached consensus. So that's what consensus is all about. So there are some fundamental properties or formal definitions to what a consensus means. So first thing is they must all agree to a common value. This is what we have been seeing so far. So there's one value, everybody agrees to it. And this value should come from one of these nodes. Should be from nodes. So it should be coming from one of the nodes participating in this consensus, right? There is no external player involved who is actually dictating the value. It should come from one of the nodes. And the third one is eventually everybody should reach a decision. So that is what termination means. Eventually all the nodes should terminate and come to a decision. It could be an agreement or it could be a disagreement, but eventually they should all terminate towards a decision, right? So that is what consensus means in the theoretical sense of it. Now let's try to understand why we need consensus. So consensus is needed in any distributed system, right? So it could be for leader election. If you have a single leader, multiple follower type of system and the leader goes down, you need the followers to use some kind of mechanism to elect a new leader. So that is where all the other nodes should agree that that new node is a leader. That is when we need consensus. We need consensus during replication. If there is a new update coming in, all the replicated nodes should agree to that value and update themselves for that node. This is also a case where we need consensus. Distributed transactions, when there are multiple systems involved, multiple services involved, all of them should agree on the status of the transaction or on the value within the transaction. And also for handling failures without inconsistency, right? So a lot of issues can happen: network issues, system issues, code level issues. There could be delays, there could be hangs, there could be so many issues. So for handling failures, also we need consensus for every node to eventually agree that, okay, there has been a failure, right? So in all these situations, we need consensus. Let's talk about a couple of types of failures. First is a crash failure, crash fault. So node can stop but cannot lie. It means that a node can be considered as a crash node or an unresponsive node, but we will not accept that the information given by that node will be a lie. We always believe that the node will always be telling the truth, right? And the other type of faults is nodes can lie, cheat, or misbehave. It can happen due to maybe concurrent transactions, maybe due to some code changes that have affected a single node, or it could be any type of misbehavior that can lead to a potential inconsistent state in the system, and these are the types of failures that consensus algorithms tend to overcome and tend to be fault tolerant towards, right? So let's see a couple of famous algorithms which are in place. First one is Paxos, second one is Raft. Let's start with Paxos and see how that works. So the time goes from left to right, and in Paxos algorithm there are some type of roles given to the nodes. The first role is a proposer role, and then we have the acceptor role, and then we have the learner role, right? Let's say there is a proposer who wants to update a value, let's say to x. Proposer wants to update some value to x. So instead of directly sending the value, first proposer will send a prepare message. You can call it message, you can call it tickets, you can call it asynchronous calls, whatever you want to call it. There is some kind of a message that is passed along to different acceptors. So there can be multiple acceptors like this, and we are sending a prepare message with some unique identifier. Let's say the identifier is 5. So all the acceptors are receiving this message asking them to prepare for something called 5, and acceptors respond that okay, we are promising that we are prepared for action 5, right? And once the proposer receives all the promises, then it will send the accept message with the exact value. So at this time we are sending for proposal 5, accept this value. So we are pushing this to all the 3 acceptors from the proposer, and the acceptors respond back with okay. So they are acknowledging that they have accepted the proposal, right? And after this point, the acceptors will pass along this message to any learner. Learner are any other systems that need to know about this change in value. It could be log system, monitoring systems, or any other nodes that need to be updated about this new value x, right? So the learn message is passed along to the learners from the different acceptors, and the learners update themselves, right? So this is how the Paxos algorithm works in general. Now let's talk about a couple of cases where a proposer crashes. So let's say proposer has asked to prepare the acceptors for hashtag 5 or proposal 5, and they have promised that they are ready for acceptance. At this point of time, let's say if proposer is crashed, after the acceptance, if proposal is crashed, then a new proposer will come into place, a backup proposal or some other node who is taking the place of this proposer, right? So at this point of time, the new proposer will check with the acceptors whenever there is a new update. So the new proposer, let's say, is pushing in proposal 6 with some new value, and at this point of time the acceptors will say, hey, I've already promised to accept proposal 5, we won't be able to accept proposal 6. At this point of time, since nobody has actually invoked the accept message from the proposer, the new proposer can actually take over and say, that's okay, you can now promise to accept hashtag 6 or proposal 6, and they will accept it, and the new proposer will actually pass along the accept message for the acceptors to process, right? So that's how the new proposal can take over from the old proposal, so that no nodes are left hanging and the system can continue. And now let's see what happens if the acceptor crashes. So let's say proposer is alive and proposer is sending prepare message to 3 different acceptors, and let's say acceptor 3 goes down. At this point of time, the proposer received 2 promises from acceptor 1, acceptor 2, but this promise has been broken. So what happens is, at this point of time, the proposer is looking for a majority. We are not going to discard the transaction. We are going to check for majority. Since we have reached 2 promises, which is 2 out of 3, we can call it as a successful attempt, and proposer can continue to process the accept messages to acceptor 1 and acceptor 2, and when acceptor 3 comes along, it can continue with the same promise and accept status as we have seen before, right? So this is how the Paxos algorithm works in general, right? Now let's take a look at Raft algorithm. So the Raft algorithm is mainly used for leader election. So let's say we have S1, S2, S3 as our three nodes, and as of now, at the beginning of time, there is no leader. So there is some kind of timeout that happens. So the nodes are checking if there is any leader. Since there is no leader, they wait for a bit and there is a timeout that happens. And when this timeout is happening, and a new election is triggered, right? Let's say this is election number 1, and S1 is the one who is initiating the election. So S1 is asking for vote for election 1 to S2 and S3. And let's say S2 and S3 are voting for S1, and now S1 is the leader. Now let's see how the replication happens. Let's say there is a client, and client wants to set x equal to 10, and this message is passed along to S1 because S1 is the leader. Now S1 is appending to its logs with log 1. Let's say this is the first log in our system, and this message is being passed along to S2 and S3 using the append message. It means that first S2 and S3, you need to update your logs in your system with this particular log message. This log message can include the timestamp, the necessary value, and so on. So this is just an updation to the log. So once they have updated their logs, they will acknowledge that, okay, for election 1, for log 1, we are acknowledging that we have received the message, right? Then the leader 1, the S1, will send a commit message. Okay, for log 1, x equal to 10 is the value, you can update it. And now both of them will respond back with okay, and S1 can respond back with okay, right? So S1 can choose to respond back earlier, or you can wait for some majority voting or some minimal voting or any kind of custom consensus that is required here. But the idea is that the message from the subnodes S2 and S3 should come back to S1, and the client will then be notified. Now let's see what happens when the leader crashes. So let's say we have client who is trying to set y equal to 20. Like before, the message is going to S1. We have appended the log. The append message is sent to the couple of other followers. The followers respond back with acknowledgement that for election 1, we have log 2, we have log 2, we are okay with it. Now what happens is the acknowledgement from S2 has reached S1, but the acknowledgement from S3 has not reached S1, and this is where S1 has crashed. Okay, and when the leader is crashed, there is some kind of a timeout setting that is available with all the nodes, and when this timeout happens, a new election is triggered, and this time let's say election is triggered by S2. So now S2 is requesting a vote to S3 for this new election. This new election is number 2. So requesting vote for number 2, S3 is voting for number 2, and now S2 is the leader. So because S2 has previously acknowledged that it has updated its log, it is just passing along that message to S3 but with a new election number. So this is the new term of the election, term 2, log 2, please append, and S3 will acknowledge that for term 2, log 2, I have appended it, and now you can go ahead and commit it. S3 has committed it, right? So this is how automated re-election happens in Raft. Let's say now S1 is back online. What happens to S1 now? It was previously the leader. Now it has come back up thinking that it is leader. Now when it comes back up, it is checking what is the current election. It was previously running the leadership role for election 1, but now it is seeing that the current term of the election is number 2. Number 2 is greater than number 1, so it needs to downgrade itself to become the follower, right? So it is now a follower, which means that now S2 can send messages to it. Now S2 is sending messages for election 2. Log 2 was supposed to happen, please append yourself, and it is acknowledging that okay, I'm going to append my log to term 2 log 2. Then the commit message is sent from S2 to S1, and the acknowledgement is coming back from S1 to S2, right? And now everybody is in sync, world is normal again. So this is how the Raft algorithm works, right? So these are the two famous algorithms for achieving consensus. So if you'd like to learn more about this consensus, if you want to go deeper into these topics, I would recommend first start with this Wikipedia page. It talks about the Byzantine faults and how different leaders, if they are misbehaving, can lead to an inconsistent system. For example, here there is an attack on some castle. If all the generals are attacking with consensus, then the battle is won. If a couple of them are misleading, then the battle is lost, right? If all generals attack in coordination, the battle is won. If two generals falsely declare that they intend to attack but instead retreat, the battle is lost. So this is the misbehavior that we talked about, right? Also look into atomic broadcast, which is kind of the fundamental behind these fault tolerant distributed systems, where we need some kind of messaging system that are going in the same order, that is the same sequence of messages, right? So this is a fundamental thing to learn about when talking about distributed consensus. Also check out this talk from Google, the Paxos algorithm, worth checking out. It goes deeper into the algorithm and the use cases and the practical examples and basics, right? So definitely check it out. So these are some resources that I would recommend for you to check out. Okay, so that's all for this video, guys. Thank you so much for watching. In the next video, let's look into clocks and see why clock synchronization is such a challenge in distributed systems. We'll talk about the different types of clocks available, and we'll see how they work to eventually get us some consensus, right? Thank you so much for watching, guys. I will see you in the next video. Do leave a like if you found this helpful. Do subscribe if you haven't done already, so that you don't miss out on any of the future videos. Thank you so much for watching. I'll see you in the next one. Cheers.